In the previous example, we had examined the flow through a packed column and where the fluid flows through voids between densely packed particles in order to maximize the contact area between the particles and the fluid for effective mass transfer, reaction, diffusion and so on. And I had defined this on the basis of the void fraction, the diameter and the velocity of the fluid through the voids between the particles. On that basis, we had defined the Reynolds number and the friction factor, and had given you a correlation, the Ergun correlation for the relationship between the Reynolds number and the friction factor. And we had also solved a problem where we actually calculated the maximum velocity for which this packed bed would be stable and the Reynolds number for that case. So, next I will look at an application in mixing. Okay. We had seen this in one of our introductory lectures. Okay. If you have a reactor, reactors will typically have an inlet and an outlet, and they will have an impeller in there for mixing. And because this impeller rotates, the fluid gets mixed. Okay. And because of that, that enhances the velocity either of the fluid which is being mixed or the particles which are suspended in the fluid, thereby enhancing the transport rates, the reaction rates and so on. Okay. And in such a configuration, it is of interest to find out what is the power required for the mixing, because that is an important consideration in design. How much power do you require, and for that power that is given, what is the additional conversion rates that are obtained because you have generated this fluid flow. Now, these impellers are they are designed for specific purposes. They have complicated shapes. They could have baffles in the tank, for example. There could be baffles on the impeller, and they could be either they could have multiple shapes of the impeller. There could be 2 blades, 4 blades, larger number of blades and so on. And for each of these, you have to find out what is the velocity profile and what is the mixing. And that is a complicated exercise. In this lecture, we will look at a simpler question, that is that if I wanted to design a large scale impeller setup, you could either try to actually calculate the velocity profiles everywhere, which is a complicated exercise. Another way you could do it is to build a smaller scale model of the impeller and try to see what is the power consumed in that scale model, and based upon that try to calculate what is the power that would be required for the actual impeller. For example, if you wanted to design a tank that was 1 meter in diameter, a priori beforehand you do not know what is the power that is going to be required. So, you design a smaller impeller tank of the same shape. All the relative length dimensions remain the same, but it is 1/10 say of the size dimension of the original tank with an impeller of 10 centimeters, and you calculate the power in that. How does the power in this smaller scale model related to the power in the actual original tank? And how fast should I rotate it to calculate the power? What is the fluid that I should use? In general, you cannot just use the same fluid. What you have to do is maintain the dimensionless groups a constant between the scale model and the actual tank. So, if I made a smaller scale model, of exactly the same shape, with an inlet and an impeller, okay, which I was rotating in the scale model, and I calculated the power in this model here. How does that relate to the power in the actual tank? Okay, how does the power in the required for rotating the impeller in the model relate to the power required for rotating the impeller in the actual tank, okay, for a given configuration. Okay. Now, rather than using the power itself, it is preferable to use a dimensionless power. Okay. So, the dimensionless power, okay, so the power, if you recall, okay, is equal to energy required per unit time. Okay. And you recall that energy is equal to mass length square T power minus 2 divided by time, okay, which is equal to m L square T power minus 3. Okay. So, that is the dimension of power. Okay. And the power can in general depend upon various dimensional quantities. Okay. So, let me write that here. Okay. Okay. So, the power okay. It can depend upon the frequency of rotation. Okay. Frequency has dimensions of time inverse. Okay. The frequency has dimensions of time inverse, okay, or the angular velocity. You recall that the angular velocity is equal to the tangential velocity divided by the distance from the center of rotation. Okay. So, that has dimensions of t inverse. Frequency and angular velocity are related by a factor of 2 pi. Okay. Okay. Angular velocity is 2 pi by the frequency, okay, because the circumference of a circle is 2 pi in radians. It can depend upon the diameter. Okay. Frequency I will call f, the power is p, diameter has dimensions of length. Okay. It can depend upon the fluid properties, the density, the viscosity, the surface tension. Okay. As m L power minus 3, viscosity mu m L inverse T inverse. It can also depend upon surface tension and gravity. Okay. The reason is because as you rotate this impeller, okay, the interface shape will change. Okay. It will be depressed at the center and it will be elevated at the circumference because centrifugal forces, and the balance between the centrifugal and the gravitational force is what determines the interface shape. So, therefore, it can depend upon gravity as well. Okay. Okay. And it can depend upon surface tension. We call that surface tension dimension is mass times t to the minus 2. Okay. So, I have one dependent group, the power, and 1, 2, 3, 4, 5, 6 independent dimensionless groups. Okay. So, therefore, I should have one, and these contain 3 dimensions, mass, length and time. Therefore, I should have one dependent dimensionless group, a non-dimensional power, and independent dimensionless groups, 3 of them. Okay. So, the power I can scale by the dimension of density, viscosity or surface tension. Okay. A priori you do not know which is the correct dimension to scale it with. If inertial forces are large, we would scale it with density. If viscous forces are dominant, we would scale it with the viscosity, and if surface tension forces are dominant, we would scale it with the surface tension. In this particular case, since the tank is large, we saw that at large scales typically inertial forces are dominant. Therefore, we will scale it with the density. Okay. So, therefore, I have to have a dimensionless group that contains the power, the density, the diameter and the frequency. Okay. And that dimensionless group, the dependent dimensionless group, is what is called the power number. Okay. And you can do it by dimensional analysis that we had done earlier, right? Express the dimensionless group as P times density power A, frequency power B, the diameter power C, and calculate those using dimensional analysis. Okay. I will not go through that. I will just tell you what the answer is. Okay. You get power divided by density into the frequency cubed into the diameter to the power of 5. Okay. So, that is one dimensionless group, okay, the power number. Okay. Power divided by the density frequency cubed d to the 5. Okay. You can see that the denominator has dimensions of mass, okay, from the density, length square because density has length power minus 3 and then diameter to the 5th power, okay, and time power minus 3 because it has frequency. Okay. I will use Fr for the rotational frequency to not confuse it with the friction factor. Okay. So, this has rotational frequency to the 3rd power. Okay. So, this is the power number, the dependent dimensionless group. What are the independent dimensionless groups? Okay. So, we have 4 effects here: density, viscosity, gravity and surface tension. So, the 3 dimensionless groups should be ratios of pairs of these. Okay. And the ratio of the density and inertia and viscosity is the Reynolds number. Okay. Rho into velocity into d by mu. Okay. Velocity has the same dimension as d times the frequency, diameter times the frequency. Okay. The velocity has the same dimension as diameter times the frequency. So, I will get rho into the rotational frequency into d square by mu. Okay. Recall that it was rho times v times d, and v has the same dimensions as rotational frequency times the diameter. So, that is the Reynolds number. The ratio of gravitational and surface and inertial forces, okay, is we had seen it earlier. It is the Froude number. Okay. This is the ratio of the inertial and the gravitational forces. If you recall, it used to be written as v by root of g d, okay, where v was the velocity. Okay. In this expression, okay, for the characteristic velocity, we substitute something with the same dimension, that is the diameter times the rotational frequency. Okay. And so, this becomes root of Fr square d by g. Okay. Once again, you can frequency has dimensions of time inverse, diameter has dimensions of length, and therefore, the gravitational force acceleration has dimensions of length per L t power minus 2. Okay. And the final one was you can the ratio of surface tension and either inertial or viscous forces. Okay. That is the Weber number. Because it is a large scale system, we will take the ratio of surface tension, inertial forces and surface tension forces. Okay. And if you recall, the ratio of inertial and surface tension forces was written as rho v square d by gamma, where gamma was the coefficient of surface tension. Okay. And for this v, we will write, okay, the frequency times the diameter. Okay. Times d, okay, which is rho the rotational frequency square d cubed by gamma. Okay. So, these are the dimensionless group that are ratios of inertia and viscosity, inertia and gravity, inertia and surface tension, and the power number has to depend on these. Okay. So, therefore, P by F r cubed is equal to some function of rho f r d square by mu. So, this is the relationship we get on the basis of dimensional analysis. Okay. And once we get these relationships for a particular value of fluid properties, the density, viscosity, surface tension, etc. Okay. For a particular frequency and diameter, okay, the relevant dimensionless groups have to be the same between the actual reactor and the scale model. Okay. The relevant dimensionless groups have to be the same between the actual reactor and the scale model. Okay. So, you cannot keep the dimensional properties the same, you have to keep the dimensionless groups the same, the relevant dimensionless groups. Okay. Relevant in the sense those that are relevant for the problem. For example, if the Weber number was large, that means that the inertial forces are much larger than the surface tension forces. So, you can neglect surface tension forces altogether and neglect the surface tension as a parameter. Okay. So, then the surface tension is no longer a parameter. Then you have to keep the Reynolds number and the Froude number the same if those are relevant, and then if you do keep both of those dimensionless groups the same between the actual and the model reactor, then the power number has to be the same. Okay. So, basically if all the parameters on the right side are the same between the model and the actual, then the left side will also be the same. Okay. You may not be able to find combinations of properties such that everything on the right hand side is the same. Okay. In that case, what is done is to include only the relevant groups. Okay. Those groups that are neither small nor large. Okay. Because if a group is either very small or very large, it means that one of those forces is not important. Okay. Therefore, you can neglect that, okay, and include only those groups that are either not very small nor very large. Okay. So, let us look at an example. Okay. The example is that I have an impeller, okay, for mixing a fluid, okay, with conditions. Okay. Okay, so, the actual reactor, okay, I take d is equal to 1 meters. So, I actually want to design a reactor with 1 meter diameter, and the frequency of revolution is equal to 1 revolution per second. Okay. Okay, that is, and I want to use a liquid with density, okay, rho is equal to 1 10 power 3 kg per meter cubed, that is the density of water, okay, and mu is equal to 1 kg per meter per second. Okay. This viscosity is large. Okay. The viscosity of water is approximately 10 power minus 3. So, what we are trying to do is to basically mix a fluid which is highly viscous, 1000 times the viscosity of water, okay, and surface tension is equal to 0.1 kg per second square. Okay. So, these are the parameters for the actual reactor, okay, and I want to model this using a reactor with diameter is equal to 0.1 meters, okay, a 1:10 scale model, okay, as far as the lengths are concerned. In that case, what is the frequency I should use? The density, the viscosity, and the gravitational due to and the surface tension that should be used, okay, so that the dimensionless groups relevant dimensionless groups are the same between the actual and the model. Okay. So, let us look at the relevant dimensionless groups for the actual reactor. Okay. Okay. So, for the actual reactor, okay, the relevant dimensionless group, the Reynolds number, actual reactor is equal to rho f r square d by mu, okay, and rho is 10 power minus 3, mu is 1, f r is 1 and d is 1. So, I get 10 power 3. Okay. 10 power 3 is a relatively large Reynolds number. Okay. Now, what is the Froude number for the actual? Okay, which will be equal to root of f r square d by g. Okay. Okay. So, the Froude number for this is approximately 0.316, okay, because g is equal to 10. So, you get square root of 0.1, which is 0.316. Okay. That is the Froude number, and the Weber number is equal to rho d square d cubed f square. Yeah. F r square by gamma. Density was 10 power 3, gamma is 0.1. Okay, so, this is approximately 10 power 4. Okay. Weber number is large, that means surface tension is most likely not important, okay, for this case. Okay, surface tension at the length scale of 1 meter and a frequency of 1 revolution per second. The Weber number is very large, so most likely this is not an important parameter. Okay. The Froude number is order 1, okay, it is neither large nor small, okay, and therefore, you have to include that as a relevant parameter. Reynolds number is 1000, okay, it is large, but not that large. Okay. As I said, even in the limit of high Reynolds number, okay, when we saw that the flow past a flat plate, for example, even at high Reynolds number, if the Reynolds number is high, you cannot neglect viscous effects because they are important for transferring momentum to the surface due to the flow that is tangential to the surface. Okay. So, therefore, I have to retain the Reynolds number also, okay, as a relevant parameter, and my power number now simplified for this particular problem where I have neglected surface tension because it is a small effect, is that power, okay, number is equal to a function of rho f r d square by mu and root of f r square d by g. Okay. So, between the scale model and the actual reactor, I have to maintain these two dimensionless groups a constant. Okay. Between the scale model and the actual reactor, I have to maintain these two dimensionless groups a constant. So, we know that for the Froude number to be a constant, the rotation rate for the actual reactor square times the d of the actual reactor has to be equal to the rotation rate of the model square times the d of the model. Okay. Okay. The Froude number is a constant because gravity cannot change. Therefore, the numerator has to be the same in the Froude number for both those cases. Okay. This implies that f r m by f r a the whole square is equal to d a by d m, okay, which is equal to 10, which implies that the scale model, the rotation rate has to be equal to square root of 10, that is 3.16 times the rotation rate for the actual reactor, rotation rate for the actual reactor was 1 revolution per second. So, this is 3.16 revolution per second. So, I have to rotate the scale model reactor at 3.16 revolutions per second, so that the Froude number is the same as that in the actual reactor. Froude number has to be the same and the Reynolds number has to be the same. Okay. The Reynolds number has to be the same. So, rho A FRA square dA square should be this. Okay, between the actual and the model reactor. Okay. This implies that rho m by mu m, okay, will be equal to FRA square dA square by FRM square dm square into rho of the actual divided by the viscosity of the actual fluid. Okay. Okay, FRM by FRA is equal to 3.16 and dA by dm is made a mistake here. Okay. dA by dm is 10. So, I have a factor of 100 and FRA by FRM, right. So, is equal to 1 by 3.16 is equal to 0.316, okay, square root of 10. Okay. So, I get 0.316 into 100 into rho A by mu A. Okay. Is equal to 31.6 into rho by mu of the actual reactor. Okay. That gives me the density and viscosity of the model reactor. Okay. Now, density of most fluids, liquids, etc., is approximately 1000 kilograms per meter cube. Okay. It does not change very much from that. Okay. So, therefore, I do not have much leeway in changing the density of a liquid. Where you have some flexibility is in changing the viscosity of a liquid. Okay. So, therefore, I can use that change in viscosity to satisfy this relation. Okay. Rho m by mu m is equal to 31.6 rho A by mu A. Okay. And if the densities I assume are the same, right, then mu A by mu m by mu A is equal to 1 by 31.6, okay, which is equal to 0.0316. Okay. Okay. So, this is the ratio of viscosities that I need to use if the densities are the same in order to have the Reynolds numbers the same, okay, between the actual and the model reactor. Okay. We know that the viscosity of the actual reactor was 1 kg per meter per second. Okay. You recall that the viscosity of the actual reactor was 1 kg per meter per second, okay, which means that the viscosity of the model reactor has to be equal of the fluid that is used in the model reactor has to be 0.0316 kg per meter per second, and the rotation rate is equal to 3.16 revolution per second. Okay. And if I use this combination of properties, the Reynolds number and the Froude number turn out to be the same. So, therefore, the power number has to be the same. Okay. Power number has to be the same. That means that for the power for the model reactor by rho of the model reactor F model reactor cubed D model reactor power 5 is equal to power of the actual reactor by rho of the actual reactor F actual reactor cubed D of the actual reactor power 5. Okay. And I said that the densities are approximately the same. Okay. So, therefore, I will get the power of the actual reactor is equal to the power of the model reactor into F A cubed d A power 5 by F M cubed d M power 5. Okay. F A cubed by d A power 5 and divided by F M cubed d M power 5. d A is 1, d M is 0.1, F A is 1, F M is 3.16. Put those numbers together and you will get a factor of 3162 times the power of the model reactor. Okay. So, if I maintain the properties in such a way that the length scales, relative ratios of all length scales are the same, the frequency is 3.16 times the frequency of the actual reactor, the viscosity is 0.0316 times the viscosity of the actual reactor, then the power that I measure in the model reactor times 3162 is going to be the power in the actual reactor. Okay. So, this is a way that you can use scale up. Okay. Do scale up. When you do scale up, you should make sure that the dimensionless groups are the same. Okay. It is not necessary to ensure that the properties are the same. Okay. If the properties are the same and the dimensionless groups change, then the power number will not be the same. So, you cannot use scale up by keeping properties the same. You have to change the properties of the fluids in such a way that the dimensionless groups are the same, and then the power of the model reactor, you can predict the relationship between the power of the model reactor and the power of the actual reactor. Okay, so, this is an example of how dimensional analysis is used for scaling up, okay, of complicated geometries. Next class we will see another example, which is of droplet mixing, okay, of breakup of droplets in a reactor. How do you scale that up? Okay, that contains a combination of the properties at the small and the large scale. We will see that in the next lecture. I will see you then.